Welcome to this explainer. You know that split second between typing in a destination and your phone magically presenting the absolute perfect route? Well, today we're peeling back that everyday map interface to dive right into the incredible mathematics of how your navigation app actually works. Spoiler alert, it's not magic, it is an absolutely brilliant application of pure math.
Here's a quick look at our itinerary for today. First, turning Earth into graphs. Then the cost of travel. Pathfinding algorithms at work. And finally, scaling up and rerouting.
Okay, let's jump right into part 1, turning Earth into graphs.
To understand how navigation works, you first have to completely strip away the physical geography. Trees, buildings, rivers, the algorithm literally doesn't care about them. Instead, the Earth is translated into this massive mathematical board game known as a graph. In graph theory, this is represented by the formula G equals V, E. This powerful abstraction translates our messy reality into just two very distinct things, vertices and edges. And this is exactly what allows algorithms to calculate efficient routes in the blink of an eye.
Let's talk about the V in that formula first, vertices, which you might also hear called nodes. Think of every physical location where a decision can be made on your commute. Basically, every single time you can turn the steering wheel to choose a new direction, bam, you're sitting on a vertex.
Now, you'd probably think vertices are only major intersections or cul-de-sacs, right? But actually, even a bend on a long, boring highway acts as a vertex. See, the mathematical connection between two nodes is a perfectly straight line. So to make the digital map preserve the curvy, physical shape of a real-world road, the system drops down these invisible intermediate nodes. Pretty wild, right?
So if vertices are the decision points, then the edges, the E in our formula, are the actual roads, paths, highways, and walkways connecting them. It's the literal asphalt you drive on to get from one decision point to the very next one. And these edges have some pretty specific rules. They can be directed, so a one-way street, that's just a single directed edge pointing in one direction. A standard two-way street is actually represented as two completely separate edges pointing in opposite directions. Plus, they're multimodal. If you tap walking on your app, you're instantly put onto a completely separate multimodal graph. A pedestrian walkway exists as a perfectly fine edge on the walking graph, but it basically doesn't exist on the driving graph.
All right, moving right along to section 2, the cost of travel. Now that our board game is totally set up, the algorithm needs a way to figure out which path is the best. It does this by calculating the cost of travel. Mathematically speaking, edges are not all created equal. Each one gets assigned a cost, or a weight. Now, static weights are just fixed physical realities, stuff like road length, speed limits, or toll booths. But Google Maps' real magic, that lies in dynamic weights. The system is constantly tweaking the weight of a road on the fly based on crowdsourced speed data, real-time accidents, active construction, and even historical traffic trends for that exact time of day.
And here's the equation they use to crunch those numbers. The Pathfinder's ultimate goal is to minimize this cumulative weight equation. Weight equals the physical distance divided by your real-time speed plus any delay costs. The really big takeaway here is that modern navigation isn't actually looking for the shortest physical distance. The weight of an edge really represents estimated travel time. It will gladly route you 5 miles out of your way to avoid a traffic jam simply because the mathematical weight of that longer, faster road is actually lower.
Which brings us to section 3, pathfinding algorithms at work. With the map fully built and weights assigned to every single road, we need the actual engines to navigate this massive web. This intimidating-looking formula right here is the time complexity for a foundational piece of computing history, Dijkstra's algorithm. Invented way back in 1956, specifically using a binary heap priority queue, it's designed to find the absolute shortest path from your starting node to all other nodes by systematically exploring the neighboring roads with the lowest cumulative weight. But there's kind of a huge catch. Dijkstra's algorithm explores uniformly in all directions, sort of spreading out like a circular wave when you drop a pebble in a pond. So if you're driving from New York to Chicago, it wastes computing power exploring roads heading south to Florida. That's exactly where the A-star search algorithm comes in. A-star evaluates nodes using a heuristic to estimate distance, meaning it acts a lot less like a wave and way more like a guided missile, which drastically optimizes long-distance routing. And here is the mathematical secret sauce behind that guided missile. A-star search uses the function f of n equals g of n plus h of n. The g is the actual cost from the start. But h is the brilliant part. It's the heuristic cost. Usually this is just the straight line as the crow flies distance directly to your destination.
Because it's always factoring in that H value, A-star cleverly avoids exploring dead ends or driving in the wrong direction. It just inherently wants to pull you closer to your goal.
Let's wrap things up with Section 4, scaling up and rerouting.
Now, A-star is fantastic, but the Earth is ridiculously huge. To figure out how this works on a global scale without melting the servers, because we're talking about billions of nodes here, modern navigation engines use something called contraction hierarchies. Basically, running standard math on billions of local neighborhood nodes is just way too slow for real-time answers. So the system mathematically simplifies minor local streets, leaving behind a sparse, super-fast network of pre-computed highway shortcuts. It's really a three-step dance. Route from your driveway to the nearest major highway, zoom across the pre-computed shortcut network, and then drop back down to the local streets right at your destination.
So we have the perfect math, totally optimized for global scale. But reality isn't perfect, is it? We've all been there. You're cruising along and suddenly, boom, an accident happens right ahead of you and traffic stops entirely. What happens then?
Well, that brings us to dynamic rerouting. Remember those dynamic weights we talked about earlier? As you're driving, if the cars ahead of you slam on their brakes, their phones instantly report that slowdown. The crowdsourced speeds drop, and the weight of that specific edge instantly spikes. If the cumulative weight of your current path suddenly gets way too high, the engine immediately triggers a recalculation. In literally milliseconds, it computes a brand new lowest weight detour and tells you to take the next exit to go right around the mess.
To summarize this absolute masterclass in engineering, here's a great observation straight from our source material. By abstracting geographical geography into vertices, nodes, and edges, pathfinding algorithms can calculate the most efficient route between any 2 points on Earth in milliseconds. The sheer genius of this system is that everything you experience physically on your drive, every red light, every weird detour, every one-way street, is actually just being mathematically crunched under the hood in real time.
So I'm going to leave you with this final thought. Tomorrow, when you take that slick little shortcut to shave 2 minutes off your morning drive, ask yourself, are you just driving on roads, or are you actually navigating a giant, invisible mathematical graph? Hopefully this explainer has totally changed how you view your daily commute, makes you wonder what other hidden matrices are running our everyday lives, right? Thanks so much for exploring with me, and hey, enjoy your mathematically perfected drive.